So let's begin today's session. And here today mainly we would be discussing about the laser measurement units, some smart grid technologies like the demand response programs, then the virtual support, etc. So mainly we would be focusing on the PMU placements. So as we all know that the PMUs are about playing a vital role in today's world. So these are the measuring devices which provide us with synchronous data, timestamp data, time synchronized data, and based on the clock pulses, these data are being delivered at a synchronous rate. So, and these are fast-acting devices, and with the base on the basis of these fast-acting devices, they aid in delivering better results or better accuracy for the power system monitoring or smart grid monitoring. So, in the present architecture of modern day smart grids, these PMUs play a very vital role, and that is the main need of using these PMUs in the smart grid context. So, since these devices are very much costly, and so on the basis of these devices, they can't be taken into account. Means their utility can't be taken into account on a larger scale. So the due to the various kind of cost limitations or cost uh, limitations, there are some limitations on the cost from the distribution monitoring side, from the transmission monitoring side. So for that, since these devices are very much costly, so for that the thing the PMUs need to be placed optimally. So that leads to the necessity of this optimal PMU placement. So firstly, we would be discussing about the purpose of optimal PMU placement. So mainly the purpose of optimal PMU placement is that uh, since we all know that I've already told that the limitation of economic means the economic limitation is a major playing a major role here, the economic limitations and infrastructural constraints. So here the installation PMU installation is limited on the basis of this okay, let's just wait. So mainly the purpose of optimal PMU placement, just 1 minute, just 1 minute. So, uh, just 1 minute. was some issues with the login ID. Any of the students joined it. Okay, it's fine. So mainly the limitation of PMU. Here we can observe that the purpose of this optimal PMU placement is due to the economic and infrastructural constraints. The critical buses. Here there are many such critical buses, generator buses, tie line buses, and these buses needs to be monitored closely, and their priorities should be given to these buses for monitoring. So these PMUs would be giving us the options for advanced controlling and monitoring actions, and these optimal bus locations need to be found out perfectly. So, as based on these above discussions, that the economic constraints and the infrastructural constraints, then the buses that needs to be monitored. On the basis of that, the optimal bus locations need to be found out, and so as to utilize the infrastructural advantages at the minimum cost. So that's the objective. So here we can observe that this is the optimal PMU placement model. Okay, so we can observe that the network data is has to be kept given. The base case DCOPF needs to be run, means DC optimal power flow. Then true results need to be found out, because based on the true results, uh, comparison can be made. True results are required for comparison of the post estimation and optimal place placement PMU results. So these two results are required to compare the outcomes. So main objective is PMU cost reduction. So here we have the state estimation constraints, observability constraints. So what is observability? That on the basis of this measurement, based on these, so based on the measurements, the entire system needs to be monitored. Entire system should have and should have measurements greater than states greater than equal to. So if this condition satisfies, then only we can say that the system is observable. Otherwise, we can't say the system is observable. Means the system will be unobservable. So with the condition of unobservability, the system state estimation. Hello? Okay. So system state estimation can't be performed. So for finding out the optimal PMU locations, these observability constraints needs to be satisfied. So this is the optimal PMU placement model, and on the basis of this optimal PMU placement model, here we can observe that these are the this is IEEE. This objective function is to minimize the PMU. So mainly the objective function is kept as objective cost minimization. Since the cost of the PMUs is high, cost minimization. This is the basic objective function. So here we can see that these buses are, after the PMU placement has been done, these buses 2, 6, 2, 6, 9 and 7. These buses are having the PMUs, and others don't require placement of PMUs, and the entire, this is IEEE 14 bus system, IEEE 14 bus system, and this is transmission system. So this is IEEE 14 bus system. So here we can observe that the we can observe that based on this placement of PMUs, these four locations 2, 6, 7 and 9, the entire system means this bus number 12, 13, 14, we can have, since PMUs can provide us with measurements uh, which are not only limited to these only voltage, magnitude and phase angles. So based on these various criteria, we can observe that the entire system means all the buses can be monitored by placing only 4 PMUs. So this is a advantageous situation. So we can also see that IEEE 13 for IEEE 13 30 bus system, 30 bus system, uh, optimal PMUs required OPP is around 7 with zero injection constraints and 10 with the non-zero injection constraints. So what are zero injection constraints? Without zero injection ZIC, without zero IC, uh, this is 7 with ZIC. So what are zero injections constraints? So these are mainly the constraints which are which leads to the condition that if you suppose there is a no injection at a bus, okay, so those buses are termed as zero injections and they can be considered as perfect measurements in the system. So those are zero injection buses. So this is various techniques are there. So here we can observe that for IEEE 14 bus system, IEEE 30 bus system, 39 bus system, 57 bus system, 118 bus system, we can observe that these are the number of PMUs 3, 7, 8, 11, 28. Means minimum number of PMUs that are at least required to make the entire system observable based on the measurements. So this is after solving this objective function, we can observe this optimal PMU placement locations or placement position number of PMUs, and we can also see it, on the basis of this we can also find out that uh, how many number of PMUs and where these PMUs should be placed. Okay, so there are various classical techniques, classical approaches. Yeah, the classical techniques can be modeled as binary linear programming. Binary linear programming. Then we have MILP, mixed integer linear programming. Then we have NLP, non-linear programming. And then we have some graph theory based approaches. Okay. So these are the classical techniques. So mainly we should depend upon these classical techniques to analyze the or finding out these optimal PMU locations. Then we have some meta-heuristic approaches. So these are mainly these particles for optimal meta-heuristic approaches. So where we have the particles form optimization, genetic algorithm, etc. Okay. So these are some meta heuristic approaches. So coming to some of the advantages and disadvantages of the PMUs. So we have the various strategies have their own limitations and advantages or disadvantages. Okay, so on the basis of their each and every strategical advantages, we can classify them as that various system has like the let us consider some integer programming. So let's consider some classical approach to integer programming. So we can observe that this is faster and also adaptable. Okay, but limitation is that with constraints being non-linear. So this is constraints. Okay, so various kinds of approaches like some meta heuristic we can also find discuss about some meta heuristic approaches. So like suppose genetic algorithm. So genetic algorithm we can these are mainly robust, adaptable, etc. But they have longer execution time. They have longer execution time. Okay. So these are there are some advantages on some part and disadvantages on some part. So uh, on the overall basis, so final conclusion that can be made is that we can incorporate architectures like contingency constraint method can deliver results in all the bus systems networks. So this can be considered as the best fit solution because they have provided results in all circumstances like the IEEE 7, IEEE 14 bus system, IEEE 30 bus system, IEEE 39 bus system, IEEE 57 bus system, as well as IEEE 114 bus system. Okay, so what we can observe is that this constraint on also binary search also delivered similar results. So this can be concluded as a matter of optimal PMU placement. Uh, Coming to this next part of this week, what is known as cyber physical system. So what we have is cyber physical system. So mainly, what do we understand about cyber physical system? So mainly, this is the outermost diagram of what a generalized overview of what is cyber physical system. So where we have the physical layer, this is the physical layer connected with the cyber layer. Okay, so how is it relevant to the power system approach? So we have this we have this in the power system domain we have these various kinds of measuring devices placed at various locations in the distribution system. So on the basis of these distribution system devices, they need to communicate uh, with the next level, means with the higher levels or the control centers, etc. So everything is interlinked. So how this interlinking is possible? It is mainly done or mainly provided by utilizing the cyber layer. So we have utilizing the cyber layer, the informations are exchanged. Okay, so on the basis of IT layer, on the basis of OT, means operation technology was prevailing in power system. But on in the basis of this new smart grid models, this OT layer has been introduced. This OT layer has been introduced along with this IT layer. So these both of them are delivering this or making this entire system a cyber physical one. So here we can observe that these are the physical entities in the present state, that is the generation, transmission, transformation, as well as transmission, then distribution, then consumers. Okay, so this is the information flow, and we have dedicated networks communication. This is the communication layer where we have the various collection system, dedicated networks, utility wired networks, wireless networks, automation systems, system data, substation automation system, etc. So based on this information flows to the server. So in the control center server, based on the in communication channels, utilizing these communication channels. So here in the control centers, various programs run: system, energy management system, supervisory SCADA system. Okay, then automatic AGC, LFC. So after these entire operation, these control signals are being generated, and based on these control signals come from this control center, and these control signals are being distributed along these physical layer components. So based on this control information, these physical layers operate. Means wherever the breaker needs to be tripped, wherever these there needs some topological changes, there needs some when suppose there are overloading in the transmission lines, distribution lines, on the smart grid point of view, uh, if there are overloading, etc. So on the basis of that, the entire system would be delivering that means whatever the information that being communicated from the control center, that information would be exchanged all throughout the physical system. So that's the overall objective of how this cyber physical system work altogether. And this is in the distribution side also, this we can observe that the distribution system here in the consumer side, since smart grid is mainly restricted to the distribution automation section, so we can mainly see that the distribution systems as well as the distribution systems as well as the isolated microgrid, these two things are highly developing in nature, developing based on these various kind of smart grid communication infrastructural advancement, infrastructure advancements. Okay, so these are highly developing. Okay, so we have various kinds of cyber physical. This is again a cyber physical components where we can see that this is the actuator. Then we have storage, processing, sensor, networking, communication, etc. So this is the different. These are the different components of these cyber physical systems. And in the physical layer, we have this plant actuator sensor. These uh, mainly in the physical layer, this plant, actuator, sensor. Then in the cyber layer, since it is a cyber physical system, so in the cyber layer we have this communication networks, some protocols, sensors, NPs, networking protocols, etc. Okay, so so this is mainly cyber layer and physical layer and cyber layer. Okay, so this is the overall overview, means overall picture of this how the systems work. And coming to some of the benefits, so benefits of using this cyber physical system. So firstly, two-way information flow, two-way information flow. Then we have coordinated operation. Then we have automated features. So these are the benefits. So two-way information flow, we can observe that here in this smart grid architecture, two-way information flow is must. So we can already have seen that the information flow is from both the distribution side as with the communication is not only unidirectional and the control strategies are not unidirectional. So there's a bidirectional information flow as well as power flow. So previously, this bidirectional, there was no bidirectional power flow either, as well as not no bidirectional this information flow. There was information. It was quite highly restricted this information flow. But by going to this present architecture of the smart grid architecture, the system normalcy that was considered as normal in those days has been reframed and reformed into a system with addition of various kinds of devices, various kinds of improvements in the system modeling, system architecture devices. Every side means the networking side, the automation side, the equipment side, everywhere there are modifications in the system. So these are mainly the benefits, and although there are some drawbacks, so which can be like we can consider that various kind of delays in communications, delays in communications. Then we can consider data drop, then cyber attacks, etc. So these data drops, so why these data drop and delays are critical, because based on these data drops, the system, uh, suppose the devices that we are presently working with, these devices, suppose these devices are not having that much infrastructural developments. So if we coordinate those systems in the present system, so on the basis of that the system, the information delay and these things uh, can be like this can take place in the present day scenario. So and to develop or to aid in such context, these delays in communication, data drop, cyber attacks, these threats should be properly maintained in the present smart grid scenario. So there had been some blackouts, like the Ukrainian blackout based on this cyber attack. So if these things are not properly monitored, then the system should would become vulnerable to these kinds of adversaries or situations. So here we have some of these cyber securities and cyber adversaries. So we have these various kinds of data manipulation attacks where FDIA, this is false data injection attacks, or here we have DOS, denial of service attack. So the FDIA is mainly restricted to the to means, to compromise these sensors, communication channel links, controllers, etc. Wherever, whereas this denial of service attack is to restrict the communication. So this can be both bidirectional attack or means here denial of service is man in the middle attack. So there can be some control liquid devices, means, or there can be a human being man who is compromising these devices and suspend the communication. And this can be both unidirectional as well as bidirectional. So mainly, suppose from the sensor point of view, and these detection strategies needs to be even needs to be means, day by day they are also means these attacks or the attackers are also developing their own strategies, so that so the people who are playing our means the control centers, the there has to be some advancements, because the similar kind of architecture won't be able to handle this kind of adversaries. So based on that, this FDIA is mainly sensor based attacks. So eh, mainly these attacks are being performed. Suppose this is the state of operation. Suppose overall or a 24 hours time interval. So if suppose there if these in the distribution side as well as the transmission side, since transmission side is quite highly monitored or highly protected, highly monitored, mainly highly monitored, and the advancements measuring devices are highly accurate, fast acting devices, PMUs are also there. So the system compromisation from by the attacker is quite limited, means it can be some they can do it, but still the attack is limited in the distribution in the transmission side. Whereas in the distribution side, whenever we consider this attack, these distribution side are very sparsely monitored, and based on this sparse monitoring, this distribution side measurements meters can be compromised. So mainly this can be done from the FDIA business false data injection attacks. So if these are the this is the suppose the state of the working state of the system. Suppose this was voltage magnitude based on time. So if suppose there is some attack, means there is some attack done by the attacker. So here suppose this would have been the operating state of the system, and suppose based on the compromisation, the attack vector, this point shifts to this point, and suppose this point shifts to this point. So that means based on this compromisation, this is the attack vector. Suppose based on this compromised value, the what will happen, the breaker on the all the devices that would see this as a state change. So that for that state change, the system is not at all prepared. So that would lead to some some maloperation. So main objective of the is to attacker attacker is willing to introduce maloperation in the system. So this is the main objective or main motive of the attacker, to introduce maloperation in the system. So if you can compromise the states, compromise the state of the system, So the attack can be enforced. And to control, to find out location, there would be a certain delay. And based on this delay, economic 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 destruction means from the power system objective point of view. So that is the main objective of this attack. So to protect these systems, so cyber security assessment needs to be performed. Cyber security assessment needs to be performed large. Okay, so that's it. Now coming to cyber resiliency. So cyber resiliency is to mainly it has two objectives: to mitigate the damage, to cyber attacks. Okay, so that's the main objective of cyber resiliency. So we have this. This is the anomaly detection strategy. So the anomaly detection methods are required mainly for the to continue with the normal operation of the system. Means although the attack would be there, means attack would uh, there would be some attack in the power system, but still the normal operating conditions should be maintained. So for that, these anomaly detection strategies need to be developed on a larger scale. And here we can see that the attack, they obviously they compromise the system. So mainly malicious command to the exciter prime mover reference settings to SCADA system. And here in the this is in the generator side, and this is in the load side. Okay, this is in the generation side, load side. So based on that, if there is a frequency imbalance due to the drop in power generation, so if there is a frequency imbalance, so what we can see is that that frequency imbalance shouldn't have occurred, because there is a increasing, there is a, suppose, constant loading scenario being maintained. So sudden increase in loading conditions, although there are not any kind of changes in the set value, neither there are changes in the loading, nor sudden loading deviations information. So information strategies should be developed. Infrastructures should be developed. And this is mainly so power system attack can be detected. Means suppose if there are no changes done from the operator's point of view, and but still there are changes being frequency deviations occurring in the generation side without any load variations, etc. So that would be delivering some that would be that would be delivering some kind of information that there have been some attack, but that attack might be of the case that there the system measurements may be compromised, the generation values or set values have been compromised, but there had been no changes done from the user point or the operator point of view. Okay, and from the load side, so suppose there is a sudden drop in load information. So demand side response command, sudden drop in load. So this would be leading to some attack being detected. So physical consequences, sudden drop in load, your malicious demand side response command. So these are mainly things that needs to be noted on the present day uh, anomaly detection strategies from the smart grid point of view. So for that, system should be cyber physical means the cyber physical system should be developed. So based on that, there are some centralized as well as the decentralized approaches. So in the centralized approach, mainly detection can be done based on the state estimation techniques. Centralized approach, state estimation based. There can be uh, chi-square test based. There can be normalized, residual based. Then binary hypothesis based. Hypothesis based, and some data driven techniques. These are the attack anomaly detection techniques, whereas in the decentralized, there are some decentralized approaches for anomaly data detection. So first can be some, or we can rather say it as SVD, singular position, SVD. And we have observer based. So these are some control strategies. So how these systems develop. These are mainly cyber physical anomaly detection technique. So these are the one. These are the ones. So first one is a centralized scheme, another is a decentralized scheme. These are the centralized approaches, and this is the decentralized approaches. Yeah. So that's it for the cyber physical information. So then we have uh, a bit of discussion. We in the lecture itself, there were a bit of discussion about the virtual and ancillary services support. So what is the virtual and ancillary support? So we can observe that in the present smart grid architecture technique, smart grid architecture models. So here we can see that this is the unidirectional power flow model. Unidirectional power flow model from the top to bottom approach. Okay, so top down approach. So, but here on the right side, what we can see is that there is a bidirectional power flow. Means there is a top down approach as well as bottom up approach. So, based on this technique, what we can see is that so here we can see that the decentralized approaches, the customers have become prosumers. So that's a major change or major advantage advancement in the system. So where we can observe that the customers, the mainly the distribution side was mainly customers that those were just consuming the power. But nowadays, with the ancillary support, these with this in the present this virtual grid system, or rather we can say the smart grid system, the the bidirectional power flow is quite a challenging task means, presently in this scenario. So based on that, the we have mainly the solar, wind. These are mainly dominant energy generating sources. So when we uh, when we hear the term solar, so there's no rotating or any rotational body. So here the solar serves as a there it doesn't have any kind of inertial support, so that it can absorb the sudden changes in the system deviations, the load variation changes, load generation, load demand. And mainly we when we have these in this one the synchronous generators, means the thermal power plants or the idle power plants, the synchronous generators, they have this they have a large rotational body. This rotational body, they have the large rotational body. So whenever there are some changes in the system loading conditions, so based on the system changes in the system loading conditions, these the sudden deviations, since the mechanical time constant is slower, so means lower, so based on that, sorry, time constant is higher, so that means the reaction is slow, or slow responding system, so it needs some time to adapt to the newer changes. So on the basis of that, the system needs some in the during this transition phase, the system needs some inertial support. So that inertial support was present if we have this 100% synchronous generator driven system. So they can during this if generation is greater than demand, less than demand. So if generation is greater than demand, there would be some frequency deviations, but that sudden frequency these deviations would be restricted. Firstly, the sudden change would be restricted by the amount of energy which is stored in the system, means or stored in the rotational body, means if the generation is more, so that would be leading to acceleration of the system. But whereas if the generation is less, that would be leading to the demand would be more in those cases. So that would lead to sudden drop in frequency. So that sudden drop in frequency or sudden uh, rise in frequency would be restricted by the inertia of the rotor. So rotor inertia. This rotor would be storing that kinetic energy or delivering that kinetic energy as per requirement so as to maintain bit of this means the sudden abrupt change. Means if the system, if there wouldn't have been any presence of these rotors, means this inertial absorbing rotor, so the frequency that shoot of the frequency from the nominal operating position to that would be, if we consider that during the absence, so this shoot can be a sudden shoot, but in the presence of these but without this inertial support, this would have been the would have been the curve of frequency shoot on without this. So there's a we can observe that there is a significant amount of delay that we can attain, and within this time if we can manage our automatic generation control, so based on that the frequency can be brought back to its nominal value. So this support is being provided by the inertia of the generators, but in the present context of smart grid inertia. So in the smart grid inertia, what we can observe that there is an absence of this rotational body. So this rotational body which can store this inertia. So since solar is a highly the solar is entirely a static device. So what can be done into the system so as to improve the system inertia? So for that, these AC/DC converters means this is the topological. This is the uh, diagram that we can see that this is the frequency control device turbine generator. This is the energy generators, energy conversion, and this is the DC exciting field. So this is fitting to the grid side. Okay, so what we can see that this is the main rotational body or the uh, energy conversion device or the generator rotating mass. So that is giving this support to maintain the frequency at a constant level. So in the similar context, we can see that here the rectifier DC voltage and AC voltage control the DC-AC converter units are the ones which can deliver means same which should, okay, because this is the system we need to design same operation as the synchronous generator. So mainly the need is that there should be some frequency support in the system. So there would be some frequency support in the system. So main aim is to provide or deliver frequency support. So here the DCAC converters, they should be designed in such a manner so that the entire system can be reframed into a virtual inertia delivering device. Okay, so On the basis of that, here we have the various kinds of inertial or ancillary support. We can see as that here the conventional synchronous generator, DFIG winds, PMSG, permanent magnet synchronous generator, PVRA. So it doesn't have any inertial capability, although these have some inertial capability, but on the basis of this synthetic inertia response with deloading and corresponding control mechanism, means there has to be some changes in the system or modifications need to be done in the system so as to make them deliver this inertia. So mainly in the around 20% of the generation is delivered of India's uh, power or active power requirement is being fed by the PVRs in India. So if this 20% of this generation doesn't have any inertia, so that would pose a high or greater challenge to the system operators. So for that thing, there in present context there the unit commitments that are generally being done in the system. Based on these unit commitments, these unit commitments are uh, done on the basis of currently to deliver this inertial support. Some units are deliberately being committed so as to give or so as to provide some inertial support to the entire system. So these are the modifications that needs to be adapted day by day basis, because these inertial support services or ancillary support services should be given by the or should be developed by the generate or should be delivered by the renewable energy systems itself. So for that, various modifications needs to be entertained on the day by day basis in future. So this is a quite interesting research domain and people are working on it also. So this is mainly the virtual synchronous generator. So how a virtual synchronous generator can be developed? So mainly we have this is the mainly the virtual the mainly the converter and inverter based improvements improvements needs to be done. So this is the main basic requirement, this converter and inverter based improvements, so that this behavior of mainly what is required is that the behavior of these synchronous generator can be fetched into this virtual synchronous generator. Means this is the actual synchronous generator. The behavior of actual synchronous generator should be fetched by this virtual synchronous generator. So what it would aid into grid stabilization, frequency regulation, frequency support, etc. So this is the main motive of delivering or developing this virtual synchronous generator at large. Now, now this is one of the interesting topics where the system demand side management program needs to be performed. So how these demand side management programs are performed? Mainly, what is demand side management that we need to understand, because based on the system requirements in the current smart grid context, firstly, this is a uh, smart grid driven code. This is a smart grid driven context. So where we can see that peak clipping, valley filling, load shifting, conservation, load growth, flexible growth. These are the objectives that need to be met. So what do you understand by peak clipping is that this is the system peak loading. Okay. So if we can reduce the peak by this much amount, and then the profile would become a flatter one. Means suppose if we have this is, let us consider that this is the peak. So if we consider for a Gaussian curve, means let us take some symmetrical, or this is an analogy that I'm trying to give because there is nowhere similar to. Suppose we have a Gaussian curve. So if we try to press from the top, then what it would happen is that this side would increase and the tip would reduce to this position. So what we can see is that there is a peak reduction. So that's the aim of peak shaving. So we can cut or trip the peak of the load. So this is peak shaving, and similar is the valley filling. So by shaving the peak, if we are rising, means suppose if this curve would have been made this profile, then the valley filling, this is called valley filling. Valley filling. So uh, this is the load shifting also. So we need to shift the load here. This is overall objective, means by peak flipping valley filling, we can obtain this load shifting, means so as to shift this point load to this section. Okay. Also conservation, means suppose we have more amount of generation. So the basis of more amount of generation, if that generation can be uh, if we can distribute that generation all throughout the system, so that generation can be, and suppose we have more amount of generation here, okay, but our demand is less. So in the present, uh, suppose we have this wind or solar. When we have this wind energy has peaks at night, whereas solar energy has peaks on day. Means these peaks are mainly from the generation point of view, not the demand point of view. From the generation point of view, the solar has the peak at daytime, the wind has its peak at during the night time. So on the basis of that wind and solar plant, let's but if the customers are not ready to take that much amount of load, means if the customers now the customers need to absorb whatever is being generated, but the customers don't have the provision because they can't suddenly increase their load demand profile, means they can't suddenly increase their load. For that, the customers need to be incentivized, and to make these customers incentivized, these control strategies, these architectures are getting their priorities day by day. So what we can observe is that these generation, the excess generation can be absorbed in the battery energy storage system so that they can be used on the later half of the day. Okay. So or based on the basis of this battery energy storage stored energy system, that can be enriched on a that can be used on the later half of the day. So various kinds of techniques like the flexible loading system. So on the basis of this, demand side management schemes are being developed. So there are some demand side management. Okay. So Okay, okay. Let's so here we have understood that the need of DSM also we need to understand what is the need of DSM. Need for demand side management. So basically, fossil fuel fossil fuel limitations are one of the primary limitations because if we continue using these fossil fuels on this rate, a day would come when these there would be the it would mark the end of this fossil fuel usage. So to increase the span of usability of these fossil fuels, these demand side programs or demand side management needs to be done on the basis of this smart grid information or smart grid architectural overview. So, secondly, we have this global warming case. Large number of greenhouse gas emissions. So if we have a huge amount of greenhouse gas emissions, so that would lead to global warming. And based on using these fossil fuels are mainly leading to these global warming scenarios. So that needs to be limited. Okay. Then we have highly uncertain, highly uncertain renewable energy devices. So these renewable energies generating devices are highly uncertain. So on the basis of these highly uncertain devices, the highly uncertain renewable devices, this demand side program needs to be given a higher priority. Okay. So since we have the uncertainty of these renewable devices are it's highly uncertain. So on the basis of that, we can't ascertain some specific value to these devices or over the generation. So if the aggregators or the distribution system operators, they need to be prepared enough. They should be prepared enough because these kind of adversaries needs to be handled with proper care or proper treatment because otherwise the system we are aiming towards the constant power flow means the constant power flow or uninterrupted power flow throughout the entire distribution side or the customer side. So for that, the systems to uh, enrich the system nature. So these things needs to be developed and every day peak demand assessment and increment needs needs to be mitigated. So mainly, these are the needs of demand side management. So let me write it using. Okay. Now we have some. demand side constraints. Before that, we have some objectives, demand side objectives. To meet these objectives, we have single objective, where single objective are mainly where the flexible devices should be brought across or shifted or brought to the actual load curve. Would be brought near the actual load curve. Okay. Or and on the second half, the 50-50% means if we consider the multi-objective, suppose if we consider the multi-objective function, so 50% for the utility side benefit and 50% customer side. So both these things will be met. So here we have the various kind of constraints also, that like device their non-negative value maintained, non-negative value maintains. So this thing needs to be done. So here we can see that this is the forecasted load curve. So this is the forecasted load curve. So what should be done? This is utility driven case. So this is for the commercial area, this is for the industrial area. Okay. So what needs to be done is that this peak should be scaled down. This peak should be scaled down and this valley should be filled up. So that should be the objective. So to suffice this objective function, mainly after performing this objective function based approach, so what the conclusion came is that the this is the this curve was being this was the aim, and what it came is that there was a significant amount of reduction. So this part came down by this much amount and this part came up by this much amount. So from the in the commercial area, after performing this demand response program, so this was the obtained value, whereas for the industrial area, this was the load curve and this was the peaks, this was the objective. So this was the aim, and the solution was quite satisfying because the solution was quite satisfying, that the demand response, this peak shifted down and this peak shifted up, but there were some fluctuations, altering situations. So this is for the single objective function based approach. This is for multi objective function based approach. So again, also here also this curve was showing this result, and this was the aim that was kept as an objective, that it should meet at least this much amount of this should be the outcome output load profile. But uh, after this objective function based approach, so what it came was this one. Means the load profile was maintained, and the profile shifted a bit. Means from this was the previous load profile, and it got shifted. So this valley got shifted a bit up, and the peak got shifted down. So this was on the positive note. This was a good system demand response program. And again, for the similar case for the industrial consumers. So for the industrial consumers, so we can observe that this was the curve, and it was quite maintained. Means this green line was maintaining. So we can observe that there is a shift in the peak point from top to down, and from the valley point from bottom to up, to a flatter profile. Means these results are delivering. Our aim is to maintain a flatter profile of the flat output profile. So these are mainly the objectives. Now, similar is case for the microgrid, where similar case of the customer participation have been considered, and this is the objective, and similarly this power profile has been met. Again, for the microgrid, this is without microgrid, and this is with microgrid, DC microgrid. So the demand response program successfully met. So this is demand side management program. So coming to the demand response program, means this is mainly the demand side management, but the demand response takes into account the customers idea. Means the customers are also playing a vital role in this demand response demand side management program. But from the demand response program, it's quite challenging that to entertain the customers uh, willingness towards this participation. Suppose based on this demand side program management program, the system, the means we need to defer the time of consumption of some essential device or equipments, but for that we need to take permission of the customer. So whether that customer is willing to shift their own time of usage, so that system or that demand response analysis, means DR, or we can say DSM DR. This is the final objective. Means both demand side management as well as demand response. The entire system constitutes the performance. Or means we need to take care of both the things. So for that, the means suppose as also in the AC, means the air conditioner loads. We have the customers also have these air conditioner loads. These there can be many various kinds of loading scenarios like washing machines, etc., light loads, etc. So these loads, like suppose the basic amenities like the light loads or the fan loads, these should be maintained. But uh, this like the critical loads, if we separate the critical loads also, because that those critical loads should be maintained also. uh, Other than that, these luxurious loads like this air conditioners load, so these things needs to be taken care of by these demand response management, like by the aggregators also, to help the customers take part in the demand response program. So main aim is to minimize the total electricity consumption. That's the main aim. And total required power generation reduction, that is also the aim. Again, idea of clean and green energy and limiting line overloading. So overloading things needs to be maintained. the system overloading needs to be maintained. So this is the entire demand response process. So we can observe that this is the blue line is delivering the energy flow diagram, whereas the red line is information flow. So ISO, independent system operator, and they are communicating with the DSOs, distribution system operators, and this is mainly done from the distribution side. So distribution of substation, and these the customers, the other residential customers, commercial customers, industrial customers, they all are delivering their information to this aggregator. So if this aggregator is again delivering or delivering this information to the DSO or to the ISO, okay. So based on such, they are based on their discussions. Finally, the distribution substation is getting information from the ISO that these things needs to be, or this operation needs to be done, and on the basis of that, this physical layer communication, that is being physical layer modifications that needs to be done by the customers itself, the or that can be done by the DSOs also, by or the control stations, based on remote side monitoring by the ZigBee communication network. So if they transfer the information, and based on that, their IoT enabled devices can be placed in the distribution side, so that they can differ the present operating scenarios of the system. So this demand response program, so like this is the aggregator side. So this is mainly the overview of the demand response program. So where firstly this ISO determines the main or total demand or and the time of operation. This time of operation is also plays a vital part. Again, the aggregator, they also receive the data from the ISOs, the data from the ISOs, and based on this, mainly the discussion what I've done now. So we have the customers like the industrial customers. So these industrial customers, they have these uh, so industrial customers, residential customers, and commercial customers. So mainly these are the industrial customers are high peak energy consumers. So mainly demand response is done to reduce the peak, peak shaving, valley filling, peak shifting, etc. These are some of the demand response objectives. So industrial customers mainly have the high peak. So the these industrial customers needs to be monitored on millisecond basis, because their changes are faster, and their changes, the loads are also highly depending on the present performance. Their loads are also highly uh, fluctuating loads, because the industrial customers have the loads of demands delivered, or the loads are of higher sizes, means the motors or the utility or the devices that they use are on a higher scale. So these are the high peak or the devices. Like now for the commercial consumers, like the air conditioning system, the industry, the like the colleges heating systems. So here there can be done, means the control strategy or the development of this demand response can be built with building energy power consumption. If that can be limited, then that can aid in the commercial uh, help, or the commercial demand response program would be improved. Now mainly the distribution system demand response program, where residential, this is the residential side, where the various devices like the refrigerators refrigerators AC, heaters, etc. So these are being placed. So systems can be means the demand response program can be entertained in such a basis that these utilities of these devices can a bit delayed, but these utility of these devices, if we need to, and suppose somebody is using their refrigerator today, so that refrigerator that is being used today, what their usage today can't be delayed to a next day scale, because that is then playing with the customer, so that people or the DSOs can't do, or the ISOs can't do. So on the basis of these requirements, these can be deferred to some bit time, like 1 hour, 2 hour delays can be incurred. So customers should be paid some incentives. So that is the main aim or main like the if we pay the customers some incentives, then the customers would be getting some amount of like they should be energized. Like if I would be keeping this equipment shut down for these long hours, then that I would be incentivized on that on some on such a scale that that would be, suppose that their power consumption would be uh, would be lifted off, means their power consumption from this time to this time would be considered as null, or would be very cheap power consumption price would be considered for this time to this time. So customers needs to be incentivized. So based on that, there should be the communication, these there could be some requirement of communication, the communication requirements, where the quality of service should be maintained, interoperability of the service should be maintained, scalability and reliability should be maintained, and security of the services should be maintained. So based on the DR's demand response, some objectives. Okay, let me write in here that demand response, demand response. So demand response objectives. So these are basic objectives that demand response, before performing this demand response program, that should be taken into within the scope of knowledge, that mainly the cost reduction. Cost reduction should be done on the basis of electricity, electricity cost reduction, and welfare maximization. So these are mainly the objective, a multi-objective function-based DR response program. So as discussed previously, that there are single objective function-based approach as well as multi-objective function-based approach. So if both maximization as well as minimization, can be done, means maximization of welfare and minimization of electricity consumption. So then this would be giving the best possible results. Means together we would be dealing with this maximization as well as the minimization program. So this serves as the objective. So here we have demand response classifications, like based on control strategies, based on price, based on load. So based on control strategy, we have centralized control, we have decentralized control, and dynamic pricing based on price, dynamic pricing, incentive and penalty based approaches, and they are based on load, like task related to DR, energy related to DR. So these are some control strategies. Now, based on the control strategies, that we can observe that here one centralized control scheme can be deployed, where the uh, here the aggregators the customers, each and every house customers are informing their informing about their role in the demand response program to the aggregators. So based on their information, the every customer, based on the every customer's information, that information is being given by the aggregators to the distribution system operators or distribution substation controllers. So based on the substation controls, uh, this is kind of centralized architecture. But if we can take into account for the decentralized control architecture, so here each and both the aggregators, eh, all the uh, all the customers are communicating amongst themselves as well as with the aggregators. So these two-way communication between these among these consumers as well as the consumer to the aggregator. So this is a decentralized approach. So where each and every individual is or do have that much amount of or do have that much suppose they do have that much amount of access, or they have that much amount of capability to control their system in a decentralized fashion, and they can control or further pass that information to the centralized controller based on the or the aggregators based and then the aggregators can further deliver that information to the centralized or the distribution system substation system. But before that, these this is a kind of bidirectional information flow from both these based on the control strategy driven approaches. So, and based on the dynamic price approach is time of use price, critical peak pricing, peak load pricing, real time pricing. These various market strategies are being developed, like the real time markets, various uh, real time markets (RTMs). These real time markets play a vital role like on the real time pricing basis. So there has to be some basis on the basis of which the system monitoring needs to be done and system uh, advancements needs to be done. Okay, so that's kind of overview of the system of this week's overview. So if you have any questions, you can ask, or then we can then go for these MCQs that I've prepared. So, which of the following is not a type of classical optimization technique? You can write it in the chat box also, or you can give the answer by switching on the mic also. So, which of the following is not a type of classical optimization technique? Not a classical type means Binary search would be the answer. Okay. So binary search would be the answer. Okay. Move to the next. The lowest minimum number of PMUs to enable full observability of IEEE 30 bus transmission system is lowest number of PMUs to enable full observability for IEEE 30 bus transmission system is. So as discussed that the optimal PMU placement is important from the present smart grid context. So why is it important? Because we can't, the cost of PMUs are quite high. So since the cost of PMUs are quite high, so the system model improvements needs to be encountered, and on the basis of the transmission system reliability, this by implementing 4 to 5 PMUs in 14 bus system, 3 to 4 PMUs it was for IEEE 14 bus system, the entire system becomes observable. So observability criteria means each and every place of the system should have uh, that much amount of facilities to monitor the entire system. So by using 4 PMUs, all the buses, 14 buses, can be monitored for IEEE 14 bus system. But the question is for IEEE 30 bus system. So it was there only. Okay, like this here. So for IEEE 30 bus system, it was 7. 7 PMUs would be there. Okay. So the answer would be 7. The answer would be 7. Then which one of the methods is exclusively used exclusively and only a distributed detection approach. So distributed detection approach, detection is, this is mainly the question is for the anomaly detection. Chi-square test, state estimation based test, uh, observer based test, binary hypothesis based test. In here the distributed detection. So I've discussed that. In the distributed detection, the anomaly detection, is, yes, these are the anomaly detection strategies where uh, for the centralized approach, we have state estimation, chi-square, normalized residual, binary hypothesis, data driven. And for the decentralized approach, we have single value decomposition, singular value decomposition, and observer based method. So here the answer is for the of distributed detection, that is decentralized detection. So for that, this observer based approach would be the correct answer. Which demand side management DSM strategy is more reliable compared to the other strategies? Uh, Load growth, peak clipping, flexible load, load shifting.
B.
B. Peak clipping. Uh, Peak clipping is one of the demand side strategies, but more reliable. So the peak clipping is not reliable one because we are just tripping the peak load point. So if we just scale down, it's- we that is being done by curtailing the load. If this peak amount of, but for that, this load needs to be shifted somewhere. So like the if we consider,
Load shifting.
yes, load shifting. So this shifting, then a peak shaving as well as valley filling, both would constitute this. This is peak shifting part, and if we do a peak shifting as well as valley filling, so this is the normal peak curve. So peak shifted down as well as valley has been filled up. So both constitute this peak shifting, load shifting. So yes, load shifting. Then which of the below mentioned DSM strategies refers to load shedding events? Load shedding events. Just discussed previously that load shedding events, load curtailments event are referred to this peak clipping point. So if we clip the peak at this point of time, means suppose if this loading above this value, if there are loading above this value, then that value would be clipped or tripped off. So based on that, we can decide that no power should be delivered if this peak value goes beyond this point. So that would be that would be giving towards or indicating towards peak clipping, because peak clipping is the main DSM strategy related to load shedding events. Then energy management strategies in DC microgrid aim to increase the stress on the energy storage system, reduce the peak energy deficit, degrade the lifespan of the energy storage, extract maximum power from the PV and wind. Mainly for the DC microgrid part, the main aim is to degrade lifespan of energy storage. This is not a possible case. Now, extract maximum power PV, that is the case, but if suppose we don't have that much amount of energy storage, means the SOC of the value, SOC of these devices are up to the full limit. So, in those cases, we can't take power with the MPPT. So, based on that, main aim is to reduce the peak energy deficit. So, this reduction is the main aim. Okay. So, critical critical difference between the demand side management DSM and DR, demand response, DSM and DR, that I've discussed previously. That what's the main difference between DSM and DR? DSM is performed at utility level, where DR is performed at both the utility and the consumer level. DR is performed at the utility level, while DSM is performed at both utility and consumer level. DSM and DR performed at utility and consumer levels. You can go with the choice. Mainly demand side management. Demand side management deals with the utility level. Okay, and DR is both the utility and the consumer level. But in this option, DR is performed at the utility. Demand response is performed, but DSM is not performed at the consumer level. This is wrong, and this is also wrong because DSM is not performed at consumer level. So only answer is this one. DSM is performed at the utility level, which is not an objective of demand response. Which of the following is not an objective of demand response? Not an objective. DR.
C.
C. Not an objective. Maximizing the electricity cost. Yes.
C is the answer. C.
Yes. 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 Thank you. Yeah. Which Which of the following holds the responsibility to provide the reference AC bus voltage and frequency in an islanded AC microgrid integrated with battery, diesel generator, EV loads, etc. So for you know that for the power system operation, the steady state operation, steady state analysis, not operation, something needs to be done, and for that something this reference,
Diesel generator.
yes, it is diesel generator. Yes, this load flow activity needs to be done. For that, the reference AC bus voltage and frequency is maintained for these all these things. PV loads, that is diesel generator is being considered. Now, a diesel generator is capable of injecting active power only. Injecting active power only, injecting active power at the cost of absorbing reactive power, always absorbing reactive power only, injecting both active and reactive power, both. So this would be injecting both active and reactive power. Which of this is not an objective of demand side management? Peak reduction, optimal scheduling of generation resources, delaying the penetration of renewable energy resources, none of the above. Not an objective function of DSM. So it would be delaying the penetration of renewable energy resources. This is not an objective function. Last question: wind turbine output power is processed to dash to feed the power to standalone DC microgrid system. Wind turbine output power
D is the answer.
This is wind turbine, a conversion strategy that is required. Wind is produced, wind generation, AC. So from that AC to make controlled AC, controlled DC feed to DC microgrid. Feeding is done to DC microgrid. So the consumer end is DC. So firstly AC to DC conversion, and then to make this DC a controlled DC, DC to DC conversion is being done. So here this answer is correct. AC DC and then DC DC. Okay. So that's it for today. So if you have any questions, otherwise we would meet on next Saturday. Thank you. Thank you very much. We will be meeting on next Saturday. I would upload these in the portal itself so that you can take reference from.